Okay, so we have a new idea now that we call concavity, which has to do with the direction that a function's graph is curving. And there are a couple of ways to interpret it that aren't all that different, really. One way to look at this is any part of a function that curves downward, like all of this curve up to about here, we say is concave down. And if it's concave down, that means that the second derivative, d squared y over dx squared, is negative. The way a lot of people remember this is that a concave down section or a negative section looks like a sad face. It curves that way. Any part of the curve that curves upwards, in other words, that looks like a happy face, is considered concave up. And in those places, we say that the second derivative must be positive. Another way you can look at this is, imagine if you were driving along this section. There'd be places along here, if you drive along this from left to right, where you would have your steering wheel turn to the right because this thing is all curving towards the right. And there are other sections where your wheel would be turned towards the left because that's the way the road is curving. And what we look for when we're analyzing this is places like this where, just for an instant, the wheel would be centered. Here you're going from turning right to turning left, and right in the middle is a place where you're in transition and the wheels are pointed straight ahead. A point like that is called an inflection, or sometimes they use POI for point of inflection. And we identify these points as places where the second derivative is exactly zero. So just as we found intervals of increase and decrease and extrema by looking for where the first derivative equaled zero, now we're going to do all that same kind of analysis but looking at the second derivative, and that will tell us about the concavity. So let's see if we can do it with this function. They give us a polynomial to start because their derivatives are a piece of cake. That was nice of them. So our first derivative is 3x squared plus 4x minus 3. We're not doing anything with that because they didn't ask about increase or decrease or extrema. We just go from there straight on to the second derivative. d squared y dx squared, or y double prime if you like. And that derivative is 6x plus 4. And we're looking for places where it equals 0. Well, this is first degree, so there's exactly one place. 6x equals negative 4, x equals minus 4/6 equals minus 2/3. So there's exactly one place where the second derivative is 0. Also, if there were any places where the second derivative is undefined, we would be interested in those as well, but this is a linear function. It's defined everywhere, so minus 2/3 is our only point of interest. And we want to know, how does our second derivative, 6x plus 4, behave around this? If x is lower than minus 2/3, let's say it's minus 10, we'd get minus 60 plus 4 is minus 56, negative number. We don't really care what the number is, just is it positive or negative. If x is precisely minus 2/3, we get minus 4 plus 4 is 0. And if x is greater than minus 2/3, let's say it's a billion, we get 6,000,000,004, which is a positive number. So that's pretty straightforward. This function is concave down, and then it inflects, and then it's concave up. And if you think about how a cubic typically looks, here's the general shape that we think of when we think cubic. It is indeed concave down for a while, and then right around here it switches to becoming concave up, and so this point would be what we call an inflection. So the intervals of concavity for this, we would say it is concave down below negative 2/3, it is concave up above negative 2/3, and there's an inflection point at negative 2/3. I'd love to just say it's at x equals negative 2/3, but when they ask for an inflection point, they probably expect coordinates. So we're going to have to plug that minus 2/3 into the function, which will be a little bit of a chore, but we'll manage. So to get the y coordinate, I'm plugging minus 2/3 into this, and we get y equals x cubed plus 2x squared minus 3x plus 1. That's minus 8/27. This is 4/9 times 2 is 8/9, and then I'm going to triple the top and bottom to get a common denominator. Here we get 6/3. Multiply that by 9 and you get 54/27. And instead of 1, we'll say 27/27 because common denominator. Negative 8 plus 24 is 16. 16 plus 54 is 70. 70 plus 27 is 97/27. And I don't think that is reducible. So the coordinates of our point of inflection are minus 2/3 and 97/27.